Okay, so today's focus is going to be finding areas between curves. So the idea that we learned in chapter 5 is actually going to be helpful in this section. So we can say that, look, we know how to find the area under a curve from chapter 5. So in other words, what we learned in chapter 5 is that if I gave you a function from A to B, we said, look, the area under this curve to the x-axis, which is, let's call this A sub 1, we learned in chapter 5 that that's the integral from A to B of f of x dx. So the definite integral of this function from A to B will give me the area under the curve to the x-axis. And we learned that in chapter 5. So now the next question is, well, what if we are asked to find the area, and let's call that area S for now, between two curves. So in other words, here's what we're saying. That is, if I were to take, let's say, two curves, and so let's, for example, say that this is the function f of x, and this is a function g of x, and what I want to do is I want to find the area between the two curves, which is this region. And see, I'm pretty confident that you guys have a pretty good idea as to how you'd find the area between the two curves. Because if we were to kind of think of it this way, we could say, look, call A sub 1 the area under f of x. So basically, A sub 1 would be all of this area, which is under f of x. And let's call A sub 2 the area under the function g of x, so basically, which is all of this area, which then you could see, then you could say, well, then the region S, the area of S, could be explained as A sub 1 minus A sub 2. And see, the good news is, from chapter 5, we could find the area under the curve of f, which is A1, and we could find the area under the curve of g, which is area 2. And so we can now define the area between the curves as the following. So we could say that for definition, the area between two curves is defined as a equals to the limit as n goes to infinity, summation I equals 1 to n of f of x sub I star minus g of x sub I star delta x. Okay, so if you remember, that's basically what we're using here. Now, look, this is the definition of a definite integral. So we know the shortcut, and we don't want to do this the long way. So I just gave you the definition, but we know the shortcut as well. So what are we basically saying? The area under the curve of f minus the area under the curve of g. Or in other words, the curve on top minus the curve on the bottom. So the area under the curve on top minus the area under the curve on the bottom will give me this area in the middle, which this is exactly what it's doing, okay? So we could say, look, unless you tell me to do things the long way, which remember x sub I star, that's our sample point and all that good stuff. But see, we're beyond that at this point. So unless we're told to use the definition of a definite integral or the definition of finding the areas between two curves, we are going to say, look, we know this as the following. And let me go on to the next page. We could say, by definition, the area A of the region bounded by the curves y equals to f of x, y equals to g of x, and the lines x equals a, x equals b, where f and g are continuous. Now remember, this is all just semantics here. Obviously, for an integral to exist, f and g have to be continuous, but what am I saying? We're trying to find the area between f and g, okay? And this is very important. F of x is greater than or equal to g of x. So this is important because what are we saying? The graph of f is always above the graph of g, or at best, they're equal for all x in the interval from a to b. This is, and see, I'm sure you guys could guess with the shortcut. What is the shortcut? The area of a between the two curves is what? The integral from a to b, and of course lower limit, upper limit, which are defined by x equals a and x equals b, which would be the area under the curve of f minus the area under the curve of g, which then this would give me the area between the curves. Now remember, it's always the curve on top minus the curve on the bottom. So that's how you find area between curves. And see, this shouldn't be anything new to us. You should be pretty familiar with this, okay? So as far as these lower and upper limits go, it all depends. Sometimes we'll be given the lower and upper limits. Sometimes we'll be told, hey, look, the functions enclose one another. So find the area between them along the enclosures. So then we would have to find the points of intersection. Okay, so remember, area between curves, between two curves, is basically the curve on top minus the curve on the bottom, integrated from the lower limit to the upper limit, which hopefully this makes sense to you, because if this doesn't, then kind of chapter 5 is probably a blur to you as well. So just remember that. We kind of talked about how we get to this. And this is the shortcut. We're always going to use the shortcut unless we're told that we have to use the definition of a definite integral to evaluate this. But we don't have to worry about that unless we're told to do so. So let's look at our first example. We're going to say find the area of the region enclosed by the parabolas y equals to x squared and y equals to 2x minus x squared. So notice for this one, what they're saying is we have two parabolas, and we're saying we want to find the area between them that's enclosed by these two parabolas. So what we notice is that they don't give us the lower and upper limits, because what they're expecting us to do is we're expected to find the lower and upper limits through where these guys close each other up, which the way they close each other up is through the points of intersection. So what we want to do is first find the points of intersection, as these will be our lower and upper limits. Okay, so that shouldn't be too difficult to do. I mean, you guys should be pretty good with this. So through substitution, what could we say? X squared equals to 2x minus x squared. And so what does that mean? We have 2x squared minus 2x equals to 0, which this implies if I factor out a 2x, I get 2x times x minus 1 equals to 0, which that means x equals 0 and x equals 1. So we could see that our lower limit is 0, our upper limit is 1. So now we need to decide what's the curve on top. And see, if you look at these guys, so if we look at this, so now we're going to say, okay, y equals x squared, we kind of have an idea as to what this looks like, right? Because y equals x squared, and I care to go from 0 to 1. If I were to kind of graph this, it'll be easy to see what's going on. But you don't have to graph this to know which curve is above the other. Because, look, this is a downward parabola. This is an upward parabola. So obviously the downward has to be above this one to kind of, for them to have areas between the curves. But if I look at this, when x is 0 for this guy, y is 0. And same thing with this. When x is 0, y is 0. When x is 1, y is 1 for this guy and that guy as well. So, but what does x squared look like from 0 to 1? It looks like that. Now, what does 2x minus x squared look like from 0 to 1? Well, if you want to have a better idea, I mean, this is a downward parabola, so it's going to look like this. So the top curve is actually 2x minus x squared. And then the bottom curve is x squared. So once we know that, once we know which curve is on top, and those are the only 2 points that they intersect each other, so I know that they'll never re-intersect each other, so I don't have to worry about that. So now what I could say is, well, this now is the integral, the area between the curves, is the integral from 0 to 1 with the curve on top, which is 2x minus x squared, minus the curve on the bottom, which is x squared dx. Okay, so once we do that, from this point on, this just falls back to chapter 5. So now we could simplify a little bit before we find the antiderivative. So what does this become? 2x minus 2x squared dx. If you want to factor out the 2 out front, just to make it a little simpler to find the antiderivative of, and then we can go ahead and integrate this. So when I integrate it, what do I get? I get 1/2 x squared minus 1/3 x cubed, and that's going from 0 to 1. And so what do I get? If I plug in 1, I get 2 times 1/2 times 1 squared minus 1/3 times 1 cubed minus, I'm not going to bother plugging in the 0 because when you plug in 0, everything zeroes out. So technically speaking, it'll be minus 0, right? I mean, all of this zeroes out. So the lower limit doesn't really affect anything here. So what does this become? This becomes 2 times 1/2 minus 1/3, which then 1/2 minus 1/3 here, what does that become? This becomes, what is that? 3/6 minus 2/6, 2 times 3/6 minus 2/6, which is 1/6 times 2, which the answer becomes 1/3. So what do we say here? Oh, so what do we say here? This area between the two curves is 1/3. Okay? So there's an example of area between two curves. Remember, we always say the area, the curve on top minus the curve on the bottom. Now, one other thing I want to point out, see, if area or if your curves go below the x-axis, such as this, don't worry about it. To find the area between the curves, see, the area between the curves will never be negative. It'll always be positive. But if you still say the curve on top minus the curve on the bottom, it'll still take care of it, because if you think about it, this is going to be a negative number, and this is going to be a negative number. But when you say a negative number minus another negative number, see, this becomes positive, and the bottom curve is going to have a larger area. So when this becomes a positive, this number is going to be bigger than that number, so the area between the curves is going to be positive. So as long as you stick to the rule of thumb where you say, when I'm finding the areas between the curves, and you don't care if the curve is above the x-axis or y-axis, as long as you say the curve on top minus the curve on the bottom, and you integrate that from your lower limit to the upper limit, that'll always give you the area between the two curves. And the area between curves is always going to be positive because of the way this is just designed. Okay, so you'll never get a negative area between two curves. Okay, now the last thing I want to talk about is if we are asked to find the area between two curves, and let's say the two curves are f of x and g of x, where f of x is greater than or equal to g of x for some values of x, but then g of x is greater than or equal to f of x for other values of x. So let's stop there for a minute. So what am I telling you? I'm asking you to find the area between two curves, f and g, and what do you notice? On the interval that you're interested, for certain values, f is above g, but then for other values, g is above f. So how am I going to find the area between the curves? So if you think about what we said earlier, I always have to say what? The curve on top minus the curve on the bottom. And then so if f and g swap where one is above the other and then the other is above the other, then I kind of have to break this up into multiple integrals. So basically, we then split the region S into several regions, which we could call S1, S2, all the way on. And then what these regions are going to have with areas A1, A2, and so on. So then the area of region S becomes the sum of A1, A2, and so on. So basically what we're saying is region S will break it up into multiple regions, and then we'll find the areas of each one of those regions. And then if we add those areas of each one of those regions, the sum will just give us the area between, or it'll give us whatever S is. So in other words, if you think about it, if I gave you something that does this, so if let's say that's F, and let me use a different color, that's F, and if this is G, what do you notice? See, from this value to this value, F is above G, but then from here to here, G is above F. So I would have to have one integral here where you say that minus that, and then a different integral here, then that minus that, and then a different integral here, this minus that, and then a different integral there for that minus that. So what we notice is once curves swap where the other one is over the other, then we have to kind of introduce a new integral. So if they never swap, like example one, notice how they only intersected each other in two places. So I just said, look, since they intersect each other at two places only, I know that one curve is always going to be above the other. But in this case, they intersect each other multiple times, which means they're swapping when one is over the other. So I would have to introduce multiple integrals. So hopefully this makes sense. I mean, this should still be easy. We just have more integrals to work with. Okay, so let's look at a second example where that will be the case, and then that should wrap up this section. So we'll say find the area of the region bounded by y equals to sine of x, y equals to cosine of x, x equals to 0, and x equals to pi over 2. So what you notice is here our lower and upper limits have been provided to us. Okay. However, here's a problem. The first thing we need to identify is, look, the first thing I should check for is, look, between 0 and pi over 2, do sine x and cosine x ever intersect each other? So basically what I'm saying here is that find any points of intersection, and this is if any, right? We may not have it. So if these guys don't intersect each other between 0 and pi over 2, then what does that mean? One is always going to be above the other, okay? So we're going to say between the curves from 0 to pi over 2. Now, if you remember the graphs of sine and cosine, and hopefully you haven't forgotten them, between 0 and pi over 2, here's what we know. See, cosine at 0 is 1, and at pi over 2 is 0. And if you remember, cosine looks like this. Okay, so that's the graph of cosine of x. And then sine at 0 is 0, and at pi over 2 is 1. So you could actually see that, and if we close this region off, because what are we doing? We're closing it at x equals 0, x equals pi over 2. And what's the area that's enclosed by 0, pi over 2, and this, which is between? It's kind of like this bow tie, right? We're kind of finding the area of that bow tie, if you think about it. But what do you notice here? Sine and cosine, in fact, do intersect each other. And if you remember, we learned from analysis that cosine of x, sine of x equals to sine of x only when x equals to pi over 4. Okay, now if you don't remember how to find this, there are multiple ways of solving for this. For example, if I were to multiply or divide both sides by cosine, what would I get? I would get 1 equals to sine x over cosine of x, and sine x over cosine x is tangent of x, and hopefully you know that the tangent of x is 1, which then x would be pi over 4. Now, if you don't know that, then I'm kind of I don't know what else to tell you, right? It just basically means that you didn't really pay much attention when you're dealing with trig functions, okay? But these are kind of, these are nice numbers that we get out of it. Sometimes they won't be as nice, and you use your graphing calculator to find them, okay? So here's what we could say. So what I know is from 0 to pi over 4, cosine is above sine. But then what do I notice? From pi over 4 to pi over 2, sine is above cosine. So how this is going to change is we are going to get, so I need to break this up. And remember, my goal is to find the area between the curves from 0 to pi over 2. However, we have a transition from pi over 4 or at pi over 4 where the curves swap. So what I'm going to say is, look, this is going to be 0 to pi over 2 f of x minus g of x dx. This is the most generic way, and remember, f is above g, but unfortunately this isn't always above g, so we have to break this up. This is going to be what? The integral from 0 to pi over 4, and from 0 to pi over 4, cosine x is above sine x, so it'll be cosine x minus sine x dx, and then plus the integral from where? Pi over 4 to pi over 2, and then that becomes sine of x minus cosine of x dx. And so what I do is I just find each of these integrals separately, which that you should be able to do from chapter 5. And then once I find them, then I add them up, and then we have our area between the curves. So what does this become? The antiderivative of cosine is going to be sine x, and then the antiderivative of sine is going to be negative cosine, which will make it plus cosine x from 0 to pi over 4, plus, we do the same thing here. The antiderivative of sine will be negative cosine x, and the antiderivative of cosine will be sine. So since there's a negative here, this will remain negative sine x from pi over 4 to pi over 2. So now we go ahead and just plug in the upper lower limit minus the lower limit for each one, and then we simplify, and then we're done. So we get sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0. So that this is that guy. And then we would say plus negative cosine of pi over 2 minus sine of pi over 2 minus negative cosine of pi over 4 minus sine of pi over 4. Okay, and now we just go ahead and evaluate this. Sine of pi over 4 is rad 2 over 2 plus cosine of pi over 4 is rad 2 over 2 minus sine of 0 is 0, so it'll be 0 plus cosine of 0 is 1 plus cosine of pi over 2 is 0 minus sine of pi over 2 is 1 minus cosine of pi over 4 is rad negative rad 2 over 2. It's negative because of that negative, and then sine of pi over 4 is rad 2 over 2, but with the negative there, we'll make it negative rad 2 over 2. And so now we just simplify. So rad 2 over 2 plus rad 2 over 2 is rad 2 minus 1 this becomes, I get another minus 1, and then negative rad 2 over 2 minus rad 2 over 2 is negative rad 2, but with that minus there, makes it plus rad 2. And so then my answer becomes 2 rad 2 minus 2. And there you have it. So this is exactly what we have. So remember, areas between curves. So just to quickly summarize what we did here, when we want to find areas between curves on an interval, you always say the function on top, the integral from my lower limit to the upper limit with the function on top minus the function on the bottom. Now, if we solve certain problems where on a certain interval, one function is above the other for certain x values, and then the next function is above the then they swap rules. Then the second function is above the first function. Then we have to break it up into multiple integrals. So every time that they kind of cross one another and the other one goes above the next one, we unfortunately have to break it up into more integrals. So in this case, they swapped once, so I had two integrals, one for this area and one for this area. Whereas in this case, I would have to have 1, 2, 3, 4 integrals, right? So the more they cross and swap, the more integrals you make. But hopefully, once you set up your integrals, the rest of the way isn't that bad because we can just integrate as needed. And of course, sometimes we may need to use the u sub, but that basically takes care of section 1. So if you have any questions, feel free to ask me.